Okay, so we're going to start out just by looking at area of a region between two curves. We've already talked about the area of the region between a curve and the x-axis. So we've already talked about how to find this area. So since this is the graph of G down here and this is the graph of F, this area that I'm writing in red, that would be the integral. Our bounds would be a and b, and then the function above would be f of x. And if we integrated that, that would give us that red area. What makes this chapter kind of just a little bit more difficult is that we also have another function. And so I'm going to put this one in blue. And so we can find the area of the blue shape, okay, by doing, again, integral a to b, this time of the function g of x. And so if you think about it, how would we use these two things to answer the ultimate question, which is what is all this area? Yeah, we'd subtract them. So if that didn't show up, let me put this in black. So we'd say minus, okay? So basically the overestimation minus the cutout or the underestimation, that would give us that area of the region between two curves. And so this is two individual integrals. If I wanted to combine it into just a single integral, I could do that using the properties of integrals that we learned way back at the beginning of chapter 4. The subtraction of two integrals is the same as the integral of the subtraction. Now, once you subtract these two things, you may need to do this by hand, you may need to do this on your calculator. We'll look at a few examples, okay? So example 2 says, what is the area of the region enclosed here? And so what we would first need to do is just graph it, okay? And so let's pretend for right now this is a non-calculator problem. Okay, so there's an x and a y-axis. I know this is the x squared plus 1, or you can just say plug in 0, you get 1. Plug in 1, you're going to get 2. Plug in 2, you get 2 squared plus 1, that's 5, so 3, 4, 5. And then we would have the same similar thing happening right over here. Whoops, I messed up there. Did you catch it? All right, so this would be up here, this would be over here. Okay, so this is the graph of y equals x squared plus 1. It's that parabola. All right, then we would also graph y equals 5, which would be this horizontal line right here. Okay, go ahead and label my x and y axis for good measure. And so what this is asking me to do is to find this area right here. Okay, so let's think about this kind of how we did the last problem, but also let's think about it in terms of something called an approximating rectangle. Okay, so to find this little rectangle, think Riemann sums. Okay, I would need to subtract the top curve minus the bottom curve to get the height. And the width is thickness dx. This is how I'm kind of going way back here to something that we did at the beginning of chapter 4. Okay, so if I multiplied 5 minus, because 5 is the top curve, minus the bottom curve, use parentheses there. Okay, so this right here is going to represent the height of that rectangle. The width of the rectangle is dx. That's the thickness. Okay, in order to add up all these rectangles, I would need to integrate, because that's what an integration symbol does. This is how we started integration, so I'm just kind of reminding you of that. We do need to know our bounds here, our x values. So x equals -2 and x equals +2, those are your bounds. Sometimes you have to do a little bit of work to find these. Okay, here it was a little bit obvious. Sometimes though you're going to have to go off to the side and actually solve the equation like this. So -1 over, you're going to see we're going to get the same answers. Square root, you get x equals ±2. All right, those are your bounds. Okay, a clear graph though, I think makes it a lot more obvious. So this is definitely something you could integrate by hand. You could also integrate it with the calculator. I'm not going to spend time in this video going over that. Whether you do this by hand and simplify, or whether you do this in the calculator, you end up getting 32/3, which is a little bit more than 10, which kind of makes sense if you kind of look at the picture and think of this as 4 and there's a triangle there. And it gives you an idea that you're on the right track. Okay, so in this next example, we're going to kind of go back to, we're not given the function. So you really have to know what you're doing here. Okay, so this a sub 1, that's representing this area. A sub 2 is representing the area over here. Keep in mind, area is always positive. An integral, though, could be positive if it's above the x-axis, could be negative if it's below the x-axis. So this particular problem we could have done back in the beginning of chapter 4. So it's just kind of here to show you it's all the same stuff. We're just talking about area underneath the curve, or trapped between two curves. All right, so just want to make it really clear. A sub 2, not negative. The integral, though, here would be negative. So let's just piece this one at a time. So let's look at that. If I integrate from -4 to 4, so starting at -4, ending at x equals 4, if I add up all that area, okay, then that's what that represents. So that would be a sub 1. And then this would be a sub 2. The area is positive, but the integral is negative. So I need to subtract that area. Okay, so this first thing that I put down here in the red bracket, that's represented by that red. I'll go ahead now and do the rest of the problem in blue, so that's kind of obvious where I got this from. So I have the -2. I'm going to go put a parenthesis here. This time I'm just starting at -1, still ending at 4. Okay, so that again would be negative a sub 2. Okay, a sub 2 is a positive area, but the integral should be negative, that number. All right, now it looks like we just need to simplify. So I've got a sub 1, I've got the minus a sub 2, and here I got a -2 times a minus, so that's a +2 a sub 2, and I can combine those so that, let me just write this down here, negative a sub 2 plus 2 a sub 2 gives me a positive a sub 2. And so if I look, there's my answer right there. So really tricky. This is really testing whether you understand the relationship between an area that is always positive and an integral that can be positive or negative. All right, let's move on to the next page. Okay, so here again we have a function and they give us a graph, so let's just go ahead and plot this graph. And for now, let's just pretend we don't have a calculator to kind of practice those graphing skills. It would not make sense to plug in a 0, a 1, or even a 2, because you would end up getting square root of a negative. So the first number I'm going to plug in is 3. 3 minus 3 is 0, square root of 0 is 0. So there's a point right there. If you recognize that this is the square root function shifted to the right 3, this also makes it easier. But if you don't recognize that, you just got to keep plugging in points. Okay, 4 minus 3 is 1, square root of that, I get 1. 5 and 6 are kind of gross because I end up getting not nice numbers. 7 would be the next number that I would want to plug in because 7 minus 3 is 4 and square root of 4 is 2. And what we end up getting is that square root function shifted to the right 3. So if you turn your head sideways, it almost looks like a half of a sideways parabola. Okay, so this wants to know, sketch the graph of f and shade the region R enclosed by the graph of f, the x-axis, that would be down here, and the vertical line x equals 6, which would be this line. So here's, I'll label that R. So the first thing they want us to do is find the area of R. This again is something we could have done earlier than this chapter. Okay, so again, I'm going to go ahead and draw this approximating rectangle. You may think you don't need it, but when we get into harder problems, this is a good thing to rely on. So the height of that approximating rectangle is the top curve, which is square root of x minus 3, minus the bottom curve, which is 0. Of course, you do not have to write minus 0. Okay, so that right there, that's the height of that rectangle. The width of that rectangle is dx. Okay, that's the thickness, that's the change in x, okay, which is pretty skinny when you're dealing with something like a Riemann sum. Okay, in order to find the area of the whole shape, we need to integrate. That's going to add up all the rectangles. We start with x equals 3, we end with x equals 6. So if you're like, I don't need to draw that rectangle in order to come up with this, that's fine, but I want you to understand it for now because we'll definitely use it later. I'm going to go ahead and just act like that minus 0 is not there. Now, if you needed to do this by hand, you definitely could. You would want to use U substitution, U equals x minus 3. Okay, and so I'm going to kind of start this, but I'm not going to finish it. Your top bound would become, well, let me just finish this. U equals x minus 3, du equals dx. The 6 would become 6 minus 3, which is 3. And the 3, which is the bottom bound, would become 3 minus 3, which is 0. Okay, so you end up having something like this. Okay, and then you do the work and everything like that. You could also type this in your calculator. It ends up not being super pretty, but you get 3.464 as a decimal. Okay, so you could do this with or without the calculator. Okay, so this says, oops, I scrolled down too far. So this says, rather than use the line x equals 6 as in part A, consider the line x equals w, where w can be any number greater than 3. All right, so I'm going to go ahead and put w right here, just to kind of, so you can kind of see it. All right, and then we're going to have this new area. So it's going to be somewhere between 0 and 3.4. That's what the area is going to be. So it says, let a of w be the area. Okay, write an integral expression for a of w. So what this is asking us to do is to just, in general, write out how we would integrate. We would still start at 3, because that's where the x value starts. But instead of stopping at 6, I would stop at w, whatever w may be. It looks like to be between 5 and 6 here, but really it could be anywhere in there. You'd still have your square root of x minus 3 here, and you'd still have dx there. So that's all I have to do there, because it just says write an expression. All right, on part D, it's saying find the rate of change of A. So hopefully by now, when you see this, you're like, hey, that means derivative. It says respect to W when W equals 6. Okay, so the first thing I'm going to do is just find A prime of W, and then I'm going to do A prime of 6. You could do this all in one step. I'm going to do it in 2 steps. So how do you derive an integral? They basically cancel out. This is like second fundamental theorem of calculus. So you're not going to derive or integrate because you're essentially doing both. So you plug in your W in for x, so you get W minus 3. If you really wanted to follow second fundamental theorem of calculus to a T, you'd go times the derivative of W, which is a 1, minus, and then you'd plug in 3 times the derivative of 3. Needless to say, this all is going to be not needed. Okay, it all cancels out. Okay, so that's the rate of change of W, A of W. So the area has a square root rate of change. Now to find A prime of 6, we're just going to plug in 6 in for W. So without a calculator, this is pretty easy to find. With a calculator, even easier. Okay? That's the final answer on D. Okay, part E says find the number B, so new variable, such that the line x equals B divides the region in part B into 2 regions with equal areas. Okay, so if I kind of come back up here and I'm going to use a new color, green. Somewhere in here, I'm going to say it looks a little bit less than 5. We're going to split that in half. And the area right here should be exactly half of the area we found in part A. So we've got to solve an equation. Okay, so this means that the area, or the integral, starting at 3, ending at b, of square root this function, square root of x minus 3 dx, that should be exactly half what I found in part A. So to finish this out, I could write this expression, or I could write actually my answer. I'll go ahead and write the answer, 3.464. Now this is an equation to be solved, okay? And so what I want to do here is kind of take this time to show you on the calculator. Let me make this just a little bit bigger. How you would do this. Okay, so I'm going to go ahead and go over how to do the 3.464. If you're like, I don't need this, then just fast forward. Okay, so first of all, if you want to do an integral, so right now I'm just recapping how we find this, just real quick. Okay, I do the integral. Okay, I do the square root, x minus 3. Close the parentheses for the square root, and then do comma x, comma 3, comma 6. Okay, and if you know you want a decimal answer, go ahead and do diamond enter. If you want an exact answer, you wouldn't need to do that. And so you can see there I've left off a decimal place. Okay, but this is accurate to 3 places. I'm going to use the more accurate answer next. So now to my problem at hand. I need to solve this equation. So that solving is a, let me make this even bigger. This is still kind of small. Solving is an algebra step. So you're going to definitely want to pick the algebra menu. And there you have solve. Okay. And I'm going to actually go up and grab this. So I don't have to type it in, except I don't want 6. I really want alpha b. Okay. So I want to know, where does that integral equal half, so I'm going to just do 0.5, times that answer. So notice I'm using there's more decimal places there. And then you remember you got to do comma. What are you solving for? I'm solving for b, so alpha b. And so that's how you get your answer with the calculator. This would not be something, although technically you could do it without the calculator, it's a stretch. So I like to just kind of go up and say, does that make sense? Yeah, that's about where I thought half would be, a little bit less than 5. So what would not make sense here is if you got something less than 3 or bigger than 6, or even close to 3 or 6. It should be somewhere in the middle, but not exactly. All right, so this next problem for sure is calculator active. Okay, there's no way to do it other than that, and you can kind of see the multiple choice answers here. Again, your first step though is just to graph, because unusual things can start happening in the graph, and we're going to look more at that in the next lesson. Okay, so use your calculator to help you graph here. I know that cosine of 0 is 1. So I know there's a point there, and I know at pi over 2, this is going to go down. It's going to look like this. It's going to be symmetrical. Okay, here's your x-axis. Here's your y-axis. I know that y equals x is the parent function that goes right through like that. What I don't know is this intersection. Okay, so the y-axis, these 3 things, it kind of looks like a triangle. It's not exactly a triangle, but this is what I'm looking for. So I'm going to go ahead and set up what I do know. I know that my lower bound is 0. I don't know what the upper bound is yet. Okay, I don't know this. I'm going to have to go off and find it in a second. I can see from my own graph that the upper bound, or the upper curve, is cosine x, and the lower curve is x. Remember, we're subtracting these, again, one more time, is because what I'm doing is I'm finding area of a little rectangle like that. So the height of that rectangle is the subtraction of your 2 functions. The width of that is always dx. Okay, so I need to go sidebar and find this thing. Actually, I'm going to use my calculator for this. So you could actually graph it, go into y equals and graph it. I'm going to go ahead and use the solve feature again though. The solve feature does not always work out really nice with trig, because there tends to be some trig problems where there are infinitely many answers. However, this one is not one of them. And again, I'm going to do diamond enter because I know I want a decimal, so I'm not even going to waste time. It gives you the little warning there might be multiple solutions. If this gives me something gross, then I'm going to have to go to y equals, okay, and actually graph it and find the intersection, which you've been doing for several years now. Don't worry if it takes you a while. Your calculator is doing a lot of work to find this. It's running through an algorithm, so it could take a while. The TI-89 titanium pluses and all that, they go faster. So here we have this. And, you know, that makes sense that that's a pretty small number because the intersection hit right away. So that x value right here is 0.739. Okay, 0.739. That's the x value. Now, this again is a rounded number, so when it comes time to actually plug this into the calculator, we go to the integrate. This is a calculus, so we go F3 integrate. And then you could go up here and grab this and edit it, although this isn't a very long equation. So I'm just going to retype it. Don't forget comma x, comma lower bound, which we know to be 0, comma. Now, if you want to go grab this number, you can. Don't just type in 0.739 if you want the most accurate answer. Because this is multiple choice, typing in 0.739, I'll lose a little bit of accuracy, but it'll be close enough to where I can figure out what the answer is. But if you're worried about accuracy, definitely go grab that number or type in all the decimal places. And so the answer is C, okay? It has to be. All right, and here's the homework. It's 3 book problems. The answers are in the back of the book.